Gennaro Abitabile, and Gennaro is giving the talk.
Okay, thank you for the introduction. This is joint work with Damsa Abusala. So we have time lock puzzle in the title, so let's start with time lock puzzles. So a time lock puzzle is a pair of algorithms, a generation algorithm that on input a time parameter t and a message m gives us a puzzle z, and then a solve algorithm that on input t and z recovers a message m. And we want the time lock puzzle to satisfy these properties. First of all, we want completeness, meaning that solve, when it's fed honestly generated puzzle, it always recovers the correct message. And then hardness, meaning that two puzzles are indistinguishable, even for an adversary that is provided with a massive amount of parallelism, but that runs in time less than t. And then we want efficiency, meaning that puzzles are efficient to generate, namely in polylogarithmic time in t, and that solving the puzzle takes polynomial time in t. So time lock puzzles can be seen as commitments, where in the commit phase, the sender just sends a puzzle to the receiver, and while generating this puzzle, it fixes the random coins. And then in the open phase, it just sends to the receiver these random coins so that the receiver can check the commitment via recomputation. So, and this commitment is perfectly binding because of the completeness of the puzzle. And then it satisfies a timed notion of hiding that directly comes from the hardness of the puzzle. But additionally, these commitments give us a feature that is the force open feature, meaning that whenever the receiver gets tired of waiting for the sender for an opening, it can solve the puzzle on its own and recover the message. However, this additional phase introduces some complication that we're going to explore in the next few slides. So the first issue I want to talk about is the well-formedness issue. So the security notion of time lock puzzles say nothing about maliciously generated puzzles. And in particular, only honestly generated puzzles are guaranteed to be solvable in time t. So I'll show you an example to see what kind of issues we can run into when we have dishonestly generated puzzle. So here we have the repeated squaring time lock puzzles, where it's not really important to look at this puzzle. I want you to focus on this value n that should be an RSA modulus, and I'm asking the question of what happens if n is not an RSA modulus. So basically, the receiver has no efficient way to determine if n is an RSA modulus or not. So we end up in an issue that is known as over-extraction, where basically the receiver will solve this puzzle and will get a value. But this value that the receiver will get is not really the committed message. Indeed, actually, this puzzle that it receives is not even a valid commitment because it doesn't have a valid opening. In particular, to see that, it's easy to notice that the generation algorithm will never output something that is not an RSA modulus. So the value that is output by gen in the third position will never be equal to n. So this commitment will never have a valid opening. So to wrap up, we would like to have well-formedness properties in which we can have a commit phase that can either be accepting or rejecting. And we want that whenever this commit phase is accepting, then the commitment has an opening with overwhelming probability, and it can be force opened in time t. Another issue that we can encounter is the public verifiability issue, meaning that whenever the receiver decides to force open the commitment and to get a message, but it wants to convince a third party, say a verifier, of this fact, it will have no efficient way to do that because time lock puzzle don't give us this feature. And in particular, the verifier will have to run a long computation to verify that M is indeed the committed message, and this is prohibitive for long time parameters. So we would like to have a solve algorithm that additionally outputs a proof. This proof is efficient to verify, and then this proof is sound, meaning that whenever the proof is accepting, then it's unfeasible to open the commitment to something else. So let's take a look at previous constructions and how do they construct the timed commitments. So they all follow a similar recipe, which they have as a key timed ingredient, this repeated squaring time lock puzzle, and they use it in a non-black box way. So what do I mean by that? That to provide the well-formedness, they use zero knowledge, and they prove that a time lock puzzle is computed correctly. And then to provide this public verifiability feature, they use some specific algebraic property of this repeated squaring time loop puzzle. So these are several drawbacks. So all of this construction, they give us different time commitments that are all based on a single family of assumption, namely repeated squaring in unknown order groups. And this is undesirable because we know we can get time lock puzzles, say, from I/O or lattices. These constructions are non-black box. For example, this step 2 to prove correctness of a time lock puzzle requires to use the code of the time lock puzzle. And they're not generic. So if we have a time lock puzzle, we don't get a recipe to turn it into a time commitment, even though these objects seem very related to each other. So a first attempt to get the well-formedness properties is to look at techniques that have been used to deal with over-extraction. So what we can do is to share the message, the sender shares the message in two shares, M0 and M1, and then it commits with the two time lock puzzles separately to M0 and M1 and sends this puzzle to the receiver, and then the receiver just asks at random to open one of the two puzzles, and it only accepts if this opening is correct. And now we have that the probability that the receiver accepts, but the unopened puzzle is not well formed, is at most 1/2. So we might hope to repeat this protocol many times to reduce this error. So, and if we do that, we end up with a protocol that looks like this, where we have in the first round several puzzles, pairs of puzzles that are sent to the receiver, and the receiver challenges one of the two puzzles per repetition. But if we do this, we end up into an issue that basically a malicious sender could decide to commit to a different message in every of the repetition. So the obvious check to this is to add a proof, like a zero-knowledge proof, that guarantees that all the messages that have been committed across these repetitions, they're all the same. But it seems that we are back at the beginning where we will get a non-black box construction, because this proof talks about computing time lock puzzles in a correct way, so it seems that we have to use the code of the time lock puzzle to prove that. But I'm going to show that we can have a black box construction, and to do that, I first have to introduce the MPC in the head paradigm. So in the MPC in the head paradigm, we have a prover that wants to prove that there exists a value x such that f of x equal y. And then to do that, this prover runs an imaginary MPC protocol for a related function f prime, for example, with 3 parties. And then this related function f prime, what it does, it simply takes the inputs of all the parties and reconstruct x, and then just checks that f of x is equal to y. So once this imaginary execution is performed by the prover just takes all of the view of these virtual parties that contain the randomness of the parties and the incoming and outgoing messages of the parties, and then starts talking to a verifier by committing to all of these views. And then there is a challenge phase in which the verifier asks for a pair of views, and basically the verifier just checks this commitment, checks that these views are somehow consistent with each other, and checks that the output of the views is 1. And this protocol was proven to be sound and honest verifier zero knowledge. And later on, it was realized that with minor modification, we can prove something a little bit more complicated. Basically, not only we prove that f of x equal y, but also that x is committed in a commitment C. And to do that, it suffices to commit to the inputs of these virtual parties in the first round. And then whenever the verifier asks for 2 views, the prover also opens the corresponding commitments of the corresponding parties that have been asked. And there is just a little additional check that the verifier is going to perform. It's going to check that these inputs are consistent with the respective views. And I want to point out that this protocol doesn't use the code of the commitment anywhere. It just verifies the commitment through recomputation, And in particular, indeed, the function of the MPC is the same as before. So by using this template, we are going to modify our protocol from before to prove that all the messages committed with puzzles across the repetitions are the same. So it's going to look a little bit like this. We'll have two common values, gamma and zeta, that will be common to all of the repetitions, and then there will be a predicate that will be proven in the MPC in the head that will ensure that all the messages are the same. So basically, the sender will sample a random value, and then it will create multiple, say, 3 out of 3 share of the message and this randomness, and each of these share is the input of a virtual part in a run of the MPC in the head. And then in the first round, it's going to commit to all of these parties' inputs. So say with the time lock puzzles. So say it's going to send lambda triplets of time lock puzzles to the receiver. And then now the receiver just sends a random value zeta that, say, it's used to define the predicate. So the predicate is defined via this value gamma that basically creates a degree 1 polynomial combining the message, the randomness committed from before, and this value sent from the receiver. And then now, the sender runs an MPC in the head execution that basically just verifies that in every of the repetition, the value gamma is computed correctly. And for some facts about polynomial, if this is the case, then with the overwhelming probability, the messages are the same across all of the repetitions. So after this is done and the prover sends the commitments to all of the views in all of the repetitions, the protocol continues as before with the receiver asking 2 views and parties inputs per repetition, and the sender replying to those. And so basically, this protocol looks a little bit like this. In the commit phase, we have lambda triplets of time lock puzzles that are sent from the sender to the receiver, and then there is a remainder part of the protocol where 2 puzzles per repetition are opened. I've colored these puzzles, for example, in red. And now, to define the open phase, it is quite straightforward. What the sender is going to do is going to open all of the puzzles that have not been opened before. And then the receiver is going to check that the majority of these puzzles are correct, and while taking the shares from the majority of the repetitions, it will reconstruct them and compute a message, and this message is the same in the majority of the repetitions. So it remains to define just the force open phase, and the force open phase just looks the same, but instead of waiting for an opening for these green puzzles, the receiver is just going to solve the puzzle by itself. So with these 3 phases, we have achieved well-forness. We are sure that whenever there is an accepting commit phase, the commitment has an opening, and we are able to force open this commitment. But still, we have to provide a proof of the force opening phase, and we still do not have that. So how do we get that? This is a very simple step. It suffices us to replace the time lock puzzles with something slightly stronger that we call quasi-publicly verifiable time lock puzzles, but they just can be constructed from time lock puzzles. So the guarantee that they require is that whenever this puzzle is honestly generated, when you run the solve algorithm, you're also going to get a proof that allows you to verify efficiently that the extracted message is the one that is contained in the puzzle. But this only holds for honestly generated puzzle. But since we have proved that an overwhelming fraction of the puzzle that we have are honestly generated, this is going to be enough for our construction. So to get that is fairly simple. To generate a puzzle, we just generate 2 puzzles. And in the first puzzle, we just encode the message, and in the second puzzle, we encode the random coins that can be used to generate the first puzzle. And then to solve the puzzle, we just solve both puzzles in parallel, and the output of the first solve execution is the message, and the other one is the proof. And then to verify, we simply take the message and the proof as random coins, feed them into the generation algorithm, and verify that we get Z1. So after having introduced this, we also get public verifiability in our construction. So to recap, the advantages of our construction is that it is black box and it is generic, meaning that you can take any time lock puzzle that you like and compile it into a timed commitment that will inherit the same time-based assumption. And in particular, we can get a post-quantum time lock puzzle, a post-quantum time commitment starting from the recently constructed post-quantum time lock puzzle. So last remarks is that in the security definitions of timed commitment, we have that the hiding lasts for a certain time t. But however, there is a little gap in the sense that this holds, this guarantee doesn't look at how many processors the adversary has, while our force open procedure that I've showed in the previous slides can extract the message in time t, but requires a security parameter number of processors to extract the message in time t. But however, in the paper, we show a different protocol, slightly different, that has a force open procedure that just requires log lambda processors. And yeah, some of you might have noticed that the underlying zero knowledge building block were only honest verifier zero knowledge, what I've showed in the previous slides, but we can lift the hiding of our protocol to be secure against malicious receiver with known techniques. So thank you for the attention.
Okay, one very short question, and then we wrap up for today.
Thank you. What I was wondering, maybe I missed something in your talk, but it occurred to me this was not specific about time lock puzzles at all, that this technique could be applied to general types of puzzles or resource lock puzzles. Did I miss something there?
Yeah, but I think that, I don't know, for example, if you look at memory art puzzles, probably this gap is going to be problematic, because if you consider the CMC, the fact that you are using more resources, it will add to the CMC. Like you will have too much CMC. While with the time, it doesn't matter the number of processors that you're using as soon as it is a polynomial number of processors. So I think that if you're using a memory time art puzzle, you need to close this gap.
Okay, thanks everyone, and see everyone tomorrow.